Okay. So my today's topic is actually about expectation and variance and probability distribution, as you can see from my heading. And you may think that this topic has already been discussed earlier. So why am I discussing it again? It is because this term moment, which is related to expectation and variance, which is connected to expectation and variance, and I'm going to say you in this particular class how this expectation and variance are connected to moment and what is moment uh, at all, and is it related to the moment which we learned in physics. Definitely the moment which we learned in physics and the moment which I am talking here right now, they are basically same thing. Okay, they are not different, but the connection between the physical movement and the statistical movement, I'm not going to discuss that particular thing. I'm going to tell you mathematically what movement is, and you please, all of the students, I'm asking all of the students to be constant, little bit to be attentive in today's class, because otherwise you'll not be able to understand, and it will be much better if you keep a copy in front of you, and if I ask you to do something, or if you can see something on the screen, so you just do some rough works, it will be much better for you. And also I'm going to discuss about probability distribution. This topic has already been covered with respect to examples, but today I'm going to discuss from core mathematical point of view. And I shall not delve into details, core details. I'll try not to make it mm, most uninteresting. I will try to give you some. I will try to make make the topic interesting to you. Okay, I know that you are engineering, you are pursuing engineering, and you may be a little bit of disinterested about core mathematics, but still, the situation is like that, and syllabus, according to the syllabus, this situation cannot be avoided. So please bear with me, and I'll try to explain the things to you clearly. So let us start with the moment about origin. Uh, the definition of moment about origin. What is it? As you can see, the nth moment about origin is, let me save the chat. Okay. The nth moment about origin of a random variable capital X denoted by mu r prime. The nth moment about origin of a random variable capital X denoted by mu r prime is the expected value of capital X to the power r, and is defined as follows mathematically. What is the mathematical expression? For discrete case, mu r prime is equal to expectation of capital X to the power r. And since we are dealing with discrete case, it can be written as summation taken over all possible values of small x, x to the power r, small x to the power r into px. And for continuous case, if we are talking about continuous random variable, then mu r prime will be denoted by expectation of capital X to the power r, which is defined as summation will be replaced by integration over entire real line, that is from minus infinity to plus infinity, small x to the power r fx into dx. Continuous random variable has not been discussed properly. It has not been discussed at all in previous classes, because continuous random variable is a topic which is there in module 2 of your syllabus. So for the time being, I am not going to discuss the continuous variable part. I am going to stick to the discrete case only. But remember, whatever I discuss about moment for discrete case is also true for continuous case, because all of you know integration, so you can judge by yourself whether I am right or wrong. And if you think that this particular formula of moment, rth moment about origin, is something new to you, that I must say that no, it is not. Last class, I discussed about variance, calculation of variance. And in the formula of variance, probably you can recall that there was a term called Ex square. Now, E of x square was calculated as summation taken over x square into px. Now you see, instead of taking 2, I have taken r. So actually the formula has been generalized in terms of r. So that is called rth moment. And Ex squared, by Keeping in mind this name, the ex squared is nothing but the second moment about the origin. E of x to the power r is the rth moment about origin, and ex squared is the second moment about origin. And here the formula, here r will be replaced by 2. So we'll get summation over x squared px. So we did the thing from the viewpoint of examples. Now I'm showing you the mathematical definition of this particular thing. And also probably you are seeing, that in front of your screen, that for discrete case I have used the notation px, and for continuous case I have used the notation fx. So you may ask me that whether both of them are probabilities or not, because p is probability, because p stands for probability. But what f is probability? The answer is yes, both of them are probabilities. Px is also probability and fx is also probability. I am using two different notations just to distinguish them from one another, one for discrete case and another for continuous case. And also, if you can remember that I told you that the probabilities associated with discrete case are known as probability mass function. Similarly, the probabilities associated with the continuous case is known as probability density function. Two names are there. Their characteristics are same. Both of them are probabilities, but the names are different, just to distinguish them from one another. One for discrete case and another for continuous case. And px, or you can say that px is a probability function, fx is also a probability function. Now, if a student thinks that let me interchange the notations, let us take fx for discrete case and px for continuous case. Can he do? Yes. Whatever notation you use, okay, you make sure that that definition is clear. If you are thinking that no, I do not like p and f, let us take m and n. You can do, but make sure that you are defining it first. Whether it is probability mass function or probability density function, that may be clarified clearly. Then whatever notation you use doesn't matter at all. And from there, there is one important note is that if I substitute r equal to 0, okay, in the definition of rth moment about origin, then you see I get mu 0 prime. And mu 0 prime is what? Expectation of capital X to the power 0. Anything to the power 0 is 1. So I am getting expectation of 1. Expectation 1 is what? 1 is a number which is constant. Okay, so expectation of 1, what will be the value of expectation of 1? Now we know that expectation of a random variable is nothing but the mean of the random variable. Now suppose I'm telling you that my age is 40. What will be my average age? Now since there is only one value, 40, my average age will also be 40. So average of a single quantity is that quantity itself. And since expectation is average, then expectation of the constant will be constant itself. Expectation of the constant will be constant itself. Okay, remember. So you are getting expectation of 1 is 1. So mu 0 prime becomes 1. Mu 0 prime becomes 1. If I substitute r equals to 1, then I'm calculating it as mu 1 prime. What is mu 1 prime? Mu 1 prime is expectation of x to the power 1. Expectation of capital X to the power 1, which is capital X. So, and now expectation of capital X will be what? By definition, we know that this is nothing but mean of the random variable x. So mu 1 prime becomes ex. So what we get? We get 0th moment about origin is 1, and first moment about origin is mean of the random variable. Very important result. Keep this in mind, and you can note it down in your copy. You can note these results down in your copy. Now let us go into the next definition. Let us move on to the next definition. You read the definition. You read the definition. What is written? Moment about the mean. Moment about the mean is defined as the rth moment about the mean is defined as the of a random variable capital X is denoted by mu r, and is defined as expectation of x minus mu whole thing to the power r. Expectation of x minus mu whole thing to the power r. What is that? Mathematically, it is defined as this. Mu r is equal to expectation of capital X minus mu whole thing to the power r. And this is defined as summation x taken over all possible values of x, and is defined as x minus mu whole thing to the power r into px. R takes values 0, 1 to up to n. That is for discrete case. For continuous case, this will be what? There is one particular mistake. There should not be any prime. This will be mu r will be expectation of capital X minus mu whole thing to the power r. Integration will be taken over minus infinity to plus infinity, small x minus mu whole thing to the power r into fx dx. Now you see, if you ask me that whether this rth moment about mean and rth moment about origin, are they connected to one another? The answer is yes. Rth moment about origin and rth moment about mean, they are connected to one another. How? In rth moment about origin, in rth moment about mean, if I substitute mu equal to 0, what is mu? Mu is mean itself. If we substitute mean to be 0, then the rth moment about mean becomes rth moment about origin. So rth moment about origin is a special case of rth moment about mean. Okay. So you note this particular definition, you write this particular definition in front of your copy, on your copy, because I'm going to scroll down and I'm going to ask you something to do so that you can do it. Okay, I'm going to scroll down further. We are going to do some calculations on this mu r. What I'm going to do, let me tell you, I'm going to substitute just like I did for rth moment about origin. I'm going to substitute r equal to 0, 1, 2 in the formula of rth moment about mean. So you just write the formula in front of you, keep the formula in front of you, and try to do this little calculation. So my question is, what happens when we substitute r equal to 0, 1, and 2 in the formula of rth moment about mean? Let us see. We get this. What am I getting? First of all, in the formula, I am putting r equal to 0. Now this becomes mu 0, and mu 0 is expectation of capital X minus mu whole thing to the power 0. Now, by definition, it is summation taken over x, x minus mu whole thing to the power 0 into px. Anything to the power 0 is 1. So I get summation over x taken over px only. And that is equal to 1 because px is the probability mass function. And therefore it is becoming 1. So what do I get? I am getting 0th moment about the mean is 1. This is another important result. 0th moment about mean is 1. You don't have to recall, you don't have to memorize these results. If I ask you in the examination, calculate the 0th moment about mean, then you calculate and find. Okay, calculate and find. So just keep the definition of rth moment about origin and rth moment about mean in mind. Just remember the definition. Do not try to remember the results. I'm just going to see why this rth moment is general case for expectation and variance. Next is, so what did I find in the previous case? I find the first moment about the origin is the expectation. Where is the variance? Let me tell you. When I put r equals to 1 in the formula of rth moment about mean, we get expectation of x minus mu to the power 1. And this is summation x, small x minus mu whole thing to the power 1 into px. Now I am breaking the summation into two halves. So I am operating the summation on the two elements. One is xpx, summation is taken over, and summation x on mu px, preceded by a minus sign. But mu is the mean, so it is constant, and any constant quantity comes out of the summation sign. So we are getting xpx minus mu into summation px. What is xpx? If you can recall, xpx is expectation of capital X. What is summation px? Summation px is 1. So I am getting expectation of x minus mu. What is expectation of x? Again, mean. And in my notation, mean is nothing but mu. So I am getting mu minus mu. which is 0. So first moment about mean is always 0. And is this result known to me, or this is a new result? No, it is not a new result, because in this result can be written as the result which I'm talking about, that is mu1, can be written as, I'm writing it over in front of you. Important result. Result is the first moment about the mean is 0, which means sum of the deviations taken from mean is 0. It's a very important result. We know it. We knew it from our school days. The sum of the deviations taken from mean is always 0. That is happening over here. That is you are getting in terms of expectation. First moment about mean is 0 means sum of the deviations taken from mean is 0. When we substitute r equals to 2, we get mu2. So we are getting e of x minus mu whole square. Summation is taken over small x. So x minus mu whole square into px. Okay. Now you break the x minus mu whole square with the formula of a minus b whole square. We are getting x square plus mu square minus 2x mu. We are operating summation on each of these three elements. So we are getting summation x square px plus mu square summation px, and 2 is constant, mu is constant, comes out of the summation sign, and we are getting minus 2 mu summation x px. Now, this is my well-known formula. Summation x square px is e of x square. We already know. Summation px is 1 because it is probability mass function. So we are writing it as what? We are writing simply it as mu square. And summation x px, we know it is expectation of x formula. So we are putting that value also. And since mu equal to expectation of x by notation, then we are getting ex square. Mu is being replaced by e of x. So we are getting minus 2 ex whole square plus ex whole square. And ultimately we are getting ex square minus ex whole square, which is the formula of variance. That is the formula of variance. So we learned from our today's first section of our today's class that the expectation and variance are the special cases of rth moment about origin or rth moment about mean. And rth moment about origin is a special case of rth moment about mean. Let us now come to the definition of probability mass function and probability distribution. Now that section has already been discussed in the in my earlier classes with respect to examples. But today I'm going to discuss them as mathematical, discuss their definition and their relevance in calculations and problems. Now, if capital X is a discrete random variable, the function Px is equal to probability of capital X into small x. When remember, we always use caps for denoting the random variables and small letters to denote the values. So here the mother variable, the random variable is capital X. It takes the value small x at different points of time. So probability that capital X takes the value small x is denoted by this notation small px. It is a function, probability function, and this function it is known as probability distribution. And this probability distribution has some properties. What are the properties? The probability distributions are satisfying the following two properties. One is Px is greater than or equal to 0 for all x. For all possible values of the random variable, the probability function is always non-negative. And if we take the summation of Px, it is 1. So if these two characteristics are satisfied, then we call this function as probability mass function in discrete case. We already know this result, but still we are again revisiting this with respect to a proper mathematical definition, because in my earlier classes I didn't give you a proper mathematical definition of this. We just discussed from the viewpoint of problems. Here comes the most important part of my today's class. There is another function which is called distribution function, or sometimes it is known as cumulative distribution function. I ask all of you to write this particular formula on your copy, because I'm going to scroll down to show you problems. And this formula, it would be much better if this formula is in front of you always, because this is the most important part of my today's class. What is distribution function? If capital X is a discrete random variable, the function given by f of small x is equal to probability that capital X takes values smaller than small x, probability of x lesser than or equal to small x, is given by the formula summation over, I'm introducing one more variable that is called small t in place of x. Previously I considered px, now I'm considering pt. Just like we changed the shape of the variable while doing integration, I'm doing the same thing over here. I'm replacing x by t, and t is such a variable which is lesser than or equal to x. This is the formula of distribution function. T lies between minus infinity and plus infinity. T is a real number. T lies between minus infinity and plus infinity means T is a real number. I'm sure that this particular definition is actually bothering you, and you are actually trying your level best to understand what is written over here. That will not be clarified until unless I show you a problem. Discussing problem will help you to understand this definition more clearly. So let us go to a particular problem. A problem is there. I have intentionally divided the problem into three halves. Okay, just to make the things easier. Okay, now if I give a long question to you, you may think that the problem is complicated, but problem is not complicated. It is a very well-known problem to you. The problem can be solved in many ways. In the morning class, I show this problem, and one boy very beautifully said that this problem can be solved by binomial distribution. I said, yes, you are right. This problem is solved by binomial distribution. But since my today's topic is cumulative distribution, so I am actually going into the explicit representation with respect to the cumulative distribution. So obviously a particular problem can be solved in different ways. So let us try to solve this problem from the discussion from the view perspective of our today's class. First part of the problem says, let there be a balanced coin which is tossed 4 times. Now list the elements of the sample space that are presumed to be equally likely, as this is what we mean by a coin to be balanced, and the corresponding value small x of the random variable capital X, that is the total number of heads. They are defining that here you are going to consider the random variable, which means that you are going to count the total number of heads one by one in the outcomes. And it is specifically mentioned that by balanced coin, what we mean? By balanced coin, we mean that all the outcomes of the coin are equally probable. In the pre-test, I gave you one example, one exercise that I told you that find the probability when the coin is the coin is balanced. What is the probability of head? You said half and half. But when I asked you what is the probability when the coin is not balanced, you could not say anything. Now remember, though we use the classical definition of probability is actually vague definition. Probabilities are not calculated. Probabilities are trust upon. So whenever I say that coin is balanced, I'm actually telling you the proportion of head and tail are same. So you can take 50% chance for head, and you can take 50% chance for tail. But when I'm saying that the proportions are not same, that means the coin is not balanced. You cannot calculate. You say that you can consider any proportion for head and tail. One can take 60% for head and 40% for tail. Another can take 75% for tail and 25% for head. Anything can happen. Okay. So by balanced coin or balanced die, we mean that all possible outcomes are equally probable. Now, since we know that a particular coin is being tossed 4 times, is equivalent to tossing 4 coins simultaneously at a time, total number of outcomes will be 2 to the power 4 and 16. 2 to the power 4, which is 16. So here I am going to tabulate, because it has been asked in the problem, I am going to tabulate all the outcomes here, all the 16 outcomes here. You try to write the outcomes by yourself. after the class is over, when we will practice the problems, you will try to tabulate all the outcomes by yourself. Now you don't have to do anything. You just keep on listening. Otherwise, it will kill time. So I have tabulated all the outcomes. Okay, 16 outcomes are there, and since all the outcomes, the coins are balanced, all the outcomes are equally probable, so the 16 outcomes individually has got probabilities 1 by 16. So I have calculated all the probabilities. I have put all the probabilities, not calculated, I have thrusted all the probabilities to the outcomes. I leveled the probabilities on the outcomes as 1 by 16. I didn't calculate it. You say the question said the points are balanced, all outcomes are equally probable. So I took the value 1 by 16 and leveled corresponding to each of the outcomes. That's what we do in calculating probabilities. That what we call calculation of probabilities. Actually, we do not calculate. And in the last column, we are counting the number of heads as has been asked in the problem. We are calculating the number of heads and we are putting the values over here. So in the first outcome, the number of head is 4. In the second outcome, it is 3. So there are 4 outcomes where the number of head is 3. Then we have some outcomes where number of heads are 2. In total, there are 6 outcomes where number of heads are 2. There are certain other outcomes where number of heads are 1. So we are tabulating it. And lastly, for TTTT, the number of head is 0. So we are putting 0. So the random variable here defines the number of heads in each of these outcomes. The number of heads in each of these outcomes. And what are the possible values of the random variable? 0, 1, 2, 3, 4. If I consider all these all these values 0, 1, 2, 3, 4 inside a set, then obviously this set is a subset of set of real numbers. So random variable, I'm again repeating, random variable is a function whose domain is the set of all possible outcomes and whose range is the subset of set of real numbers. My first part of the problem is done. Now the second part of the problem. Second part of the problem says, find a formula for the probability of the total number of heads obtained in 4 tosses of a balanced coin. So we calculate each of the probabilities. First, my probability, I'm calculating probability of x equal to 0. How many outcomes are there? How many times x is taking the value 0? Only once. So the probability is 1 by 16. How many times probability the random variable takes the value 1? 4 times. If you see the chart, then it should be 4 by 16, 1 by 16 plus 1 by 16 plus 1 by 16 plus 1 by 16. For x equal to 2, it is 6 by 16. For x equal to 3, it is 4 by 16. And for x equal to 4, it is again 1 by 16. H. Now, if you carefully look into this, here the probability function is given by the formula 4cx by 2 to the power 4. This is my function, probability function formula. And here x takes the value 0, 1, 2, 3, 4. You can verify by yourself. Okay. Here comes the most important part which I'm going to show you right now. I'm going to find the distribution function for the corresponding problem. Okay, that is the most important part. So my distribution function is what? Is given by the formula fx, where fx is probability of x less than or equal to small x. The main part which is creating problem is that t, because I have introduced it forcefully. So I have to clarify what t is. Okay, let us calculate. Be careful. First of all, I am putting x equal to 0. So I am getting f0. F0 means by the formula it is probability of x less than or equal to 0. And that means by the formula it is summation pt, where small t is less than or equal to 0. T is a value which is discrete. And here I am saying that t is less than or equal to 0. Then there is only one possibility, that t is equal to 0. I am putting this over here. So p0 is becoming 1 by 16. When I am putting x equal to 1, that means probability of x less than or equal to 1. By definition, here t is taking values less than or equal to 1. So there are two possibilities for t, 0 and 1. So I am putting p0 plus p1, which is 5 by 16. Similarly, for x equal to 2, T is taking value less than or equal to 2. Three possibilities. So I'm calculating them as 11 by 16. For, for x equal to 3, I'm putting 3 over here. And by the formula, small t is less than or equal to 3. So how many possibilities? 4. T equal to 0, t equal to 1, t equal to 2, t equal to 3. So I'm calculating this as 15 by 16. And lastly, for t less than or equal to 4, there are 5 possibilities. So I'm calculating this as 1. And since I'm getting 1, this indicates my calculation is all right. Why? Because cumulative distribution is not a new thing. Previously in school, you learned about frequency chart and you learned about frequencies and cumulative frequencies. You very well know that what is cumulative frequency. And also you know the total frequency is same as the last value of the cumulative frequency. Just like that, here the total probability, which is 1, is equal to the last value of the cumulative probability. And my cumulative probability is coming to be 1. My cumulative probability is coming to be 1, which is obviously equal to the total probability. And therefore it says the entire calculation is wrong. But if you are not getting 1 over here, that means you have done some mistakes somewhere in the calculation. I shall be sharing this note in the Google Classroom and I will be uploading the video in the YouTube. So if you are finding any difficulties, you can revisit them again and again. My video again and again to clarify the thing. But you have to do the calculations by yourself. Otherwise you shall not be able to understand. On Wednesday, when I shall be taking your class, I shall be again discussing this cumulative distribution function with one or two problems, so that the things you actually understand what I mean to say over here. Now, these are the values of the distribution function. My distribution function is fx. These are the values, different values of f or corresponding values of x. But this is not in its function form. Let us write the distribution function in the function form. And if we do so, we are getting this. This is my distribution function. So fx equal to, when small x is less than 0, when small x is less than 0, that means what? T is less than or equal to x. Your x is less than 0. That means what? T is less than 0. That is what? 0. So fx is 0 when x is less than 0. When x lies between 0 and 1, when x lies between 0 and 1, that means what? X lying between 0 and 1 means x is discrete, so x equal to 0. There are no other possibilities. Although I am writing it as interval, that doesn't mean it is continuous. I am considering the discrete case, so x is lying between this, but x has only one possibility, that is x equal to 0, and therefore t equal to 0, and therefore it is 1 by 16. When I am writing x equal lying between 1 and 2, then I am writing it as 5 by 16, and then 11 by 16, then 15 by 16, and so on. When x greater than or equal to 4, I am writing it as 1. Try to find this function by yourself. Okay, then this will be clearer to you. Okay, so this is the distribution function of the given coin tossing problem. There are two very important formulae regarding the distribution function. These are the formula. You just read it. Okay, when you will get the note. I am not going to discuss this formula right now because regarding this formula, I am going to do some calculations in the next class. Today, I am not considered any problem with respect to this particular formula. This particular formula will be discussed in our next class. Okay, distribution function. And that is another important formula. These formula have been written from I have considered this, I have taken this formula from the book which I've shared with you, the John Fund book. Okay, there you can also get the formula present. And lastly, there is another problem. I am reading the problem for you. This problem is, suppose that a day's production of 850 manufactured parts contains 50 parts that do not conform to customer requirements. 2 parts are selected at random without replacement from the batch. Let the random variable capital X equal the number of non-conforming parts in the sample. What is the cumulative distribution of function of capital X? I have solved this problem for you. It is not a homework. I have already solved this problem. So you also go through the calculation and you try to solve it by yourself and try to find the distribution function also. I have shown the distribution function over here, But with, first of all, you try by yourself, and then you, if you find any difficulties, you verify with my calculation. So this much for today. I'm going to end my today's session over here. Okay, but one thing I must tell you, that I shall be online for this session. I have, the countdown has already begun. The session is going to end soon. But if after the session ends, I will rejoin. I will rejoin, and I shall be waiting for you. If you think that you have any doubt regarding my today's discussion, then you can again rejoin, and you can ask me questions. Okay, so I shall be, after the session ends, I will be waiting for you for 5 minutes after rejoining. And another thing I must say, I am almost done with my module 1 syllabus, and that was our agreement, that module, after the completion of module 1 syllabus, I am going to take one quiz test of 10 marks. So I shall notify the date. I'm going to prepare the question, and I'm going to notify the date to you, and you are going to give the examination through Google form. Okay, and my entire question is based upon the notes which I've shared with you, nothing beyond that. Okay, the notes, the problems will be from my notes. So you just start studying, because soon there will be examination. So please, my class today ends over here, but if the session ends, you rejoin, and if you have any doubts, you can ask me, because I shall be online for 5 minutes more. So thank you so much.
Thank you, sir.
Yeah, okay.
Thank you, sir.
Thank you, sir.